All right, welcome back. This is video number 3, and we're going to be taking a look at making all this code that we coded last video into something that's more object-oriented so that we can create more than one layer at one time and do it with relative ease. So in like a couple lines of code, we can create like 7 or 8 layers, right? Rather than having to go through this every single time, having to manually code like connections between the layers. That is what we're going to be focusing on today. And it'll be going a little bit faster than normal, as there is an expectation that everybody at least take a look at what object-oriented programming is, and everybody that's watching has at least a little bit of experience in coding with uh, object-oriented programming. So I know you guys are probably getting sick of me saying saying object-oriented programming, but it is what it is. We'll start off by creating a class that defines what the layer generator is going to be. So we'll call it layer gen, and we need to initialize this class, right? So we'll initialize it with whatever we're going to define a layer to have, right? So what does a layer have? It has inputs coming into it, and wait, it has neurons in it, right? Inputs coming in and neurons. Uh, yeah, that's pretty much mhm, that is exactly what it is. All right. So we can create two variables called uh inputs, just name it inputs, and then we'll do neurons. But we're actually looking at the number of inputs, so we can do uh num inputs and num neurons, right? All right. So we go ahead and all right. So in this initialization, we'll also have to kind of create the weights and biases, right? So we didn't create weights. We didn't add the weights and biases up here because what we want to be able to control, right, as like the creator of this layer, is simply the number of inputs and the number of neurons. As we went over earlier, we don't want to touch the weights and biases, right? We want to initialize them all to random values or zero. We, as the creator, will never personally go in and manually tweak any of the weights or biases. We let the computer handle that. So there should never be a time in which we'll ever need to give this function, right? Any number of weights or biases. So we give it how many inputs there are, yes, and we give it how many neurons there are, but we'll never give it the specific weights and biases. All right, so that's what this line of code is going to be doing. It's going to be pretty much initializing our weights, uh, because it isn't a part of one of the parameters we set or we give to this function, right? So we have to kind of initialize it. So to do that, we'll be using a NumPy function, right? And like that NumPy function uh pretty much generates random numbers for us. And before we do that, we have to do something it's like kind of like a prerequisite for using this thing. And we pretty much have to set the seed for our random number generator. So what that means is that all the random numbers it generates is going to be based off of this seed right here, right? So whatever, if you set this seed to equal 0, no matter what device you're on, you're still going to get the same random numbers if you run this, right? So what that does for us is it allows you guys at home to set the seed to be 0 and get the same numbers that I do, so that you guys can check to see if your outputs are equal to mine, to see if you to just like follow along and like uh verify the code that you've been working on, right? So that's what does that do right there? All right, there we go. All right, so that's what that pretty much does. A random seed set to 0, right? So now we can actually use the NumPy random function, random.rand. So we'll do np.random.rand, and then it'll ask us like how many numbers. So like it'll ask us for the shape. So how big do you want the set of random numbers to be, right? So we want it, right? So our weights, right, are dependent on the connections between the inputs and the neurons, right? So the shape is pretty much dependent on the inputs and neurons. So when we define the shape of uh, the array of random numbers it returns, we want to use the inputs and neurons to determine the shape, right? So we can give it these values by just putting num inputs as well, as well as num neurons. And sorry if you guys can hear my dog. She's kind of barking right now. I have no idea why. So why did I do that? There we go. So this is what our weights are going to be set to. We got to do the same thing for the biases as well. But in this scenario, we can either randomize the biases or just set them all equal to 0. And just for educational purposes, we won't do the same thing we just did. We'll do something else. So we'll be setting all the biases to equal 0. And we can do that by using a NumPy function as well. And that's called np.zeros. So when you call this, right, it also asks for this shape. So we have one layer, so we're modeling it one layer at a time. So we have one one is the initial shape, and then we have num inputs, or num neurons actually, that determine how long how many biases we have, right? Because the number of neurons is what determines how many biases we have. So it starts from 1, so it assumes we have 1 neuron, and then it makes however many, up till however many neurons we specified. So if we put 3 for the number of neurons, it'll make random biases for 1 through 3 neurons, if that makes sense. So if we want, we can go ahead and actually kind of like run these outside just to see what they output. Oh, why does it keep doing that? It's like highlighting and permanently staying there. Okay, so why don't we go ahead and like run this actually. We don't want this to be in that block. And not that block either. Alright, so there's no self. Oh. Alright, so why don't we do this? Why don't we just print this out? But before we do that, we have to specify what these values are, right? Because we're not in the class anymore, so we have to just give it temporary values. So num inputs is equal to, let's see. So how many inputs do we want? We want, let's say 5 inputs, okay? And then we have num neurons, and that can equal, let's say we have 10 neurons, okay? So if we run this, there we are. Can I interpret 10 as a data type? Why can it not? This is a part of troubleshooting. Oh, it's asking for the shape. That is why I see the part issue. Perfect. Okay, so we forgot the extra parentheses because the shape itself has to be in parentheses. So after if we run this, it should work. There we go. Perfect. So these are our biases. We have 10 of them because we have 10 neurons, and we initialized them all to be 0, right? So there should be 10 zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 zeros. Perfect. And then we should have this is our connections per neuron. All right, and then we should have around 5 of these big lists with 10 individual weight values inside of it, right? Because that's how we define the size. We base it off of the inputs of neurons, and the input size is 5, the neuron size is 10. So there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them in each of these. So if you want to make it a little bit more visually appealing, we can go ahead and like reduce this number down to like 3 maybe. Not 23, 3. Alright, and that should look much better. So we have 5, 1, 2, 3, 4, 5, 5 inputs with 1, 2, 3, 3 respective weights. per connection between the inputs and the neuron, right? So these three values right here, they represent each neuron. So this column, this first column right here, that's one neuron. The second column in the middle, that's another neuron. And the third column is also another neuron. Each of the rows is an input. So this is input 1, input 2, input 3, input 4, input 5, going all the way down. And the columns are the neurons. Okay, so now that we have that underway, we can go ahead and erase this. I don't really care about this anymore. It was just to help visualize it. So now that we have our values, that we've initialized what a neuron is and the weights and biases for that neuron, we can start programming a forward pass, right, like we did earlier. This would pretty much be us making the equation for the output in object-oriented format. So we can just create a method, and I'm not sure if I explained it already, but the def in Python stands for, it's basically just a method. If you've worked with Java, it's basically just a method. Let's just leave it at that for now. So forward self and inputs. All right, so we'll have to work with our global variable output. So we do self.output equals np dot we're taking the dot product, yes, of the the inputs and the weights, right? So we'll have to really specify what the inputs are, right? But we already have that. So whenever we do the forward pass, we'll be giving it inputs as well. So we can just go ahead and add that. And then we also have the global variable weights. So we can go ahead and call weights as well. And if you're confused as to why I'm using self and then calling the variable, it's because setting the variable to be self allows it to be called from any method inside the class. So it just makes it kind of like a global variable as compared to like this inputs. You can't call this inputs from any other place other than forward. So if that makes sense, hopefully it does make sense. So we have the weights, and then at the end we add the bias, right? That's the and that is pretty much our forward pass completed, right? So we have yeah, this looks right. So we have we're giving the forward pass inputs when we call it, and then it'll return or it'll update the output value to be the dot product between the inputs that we give it and the weights that it has initialized randomly. And then we add the bias to that, or the biases for however many neurons we created, right? So this is dynamic. Notice how this is kind of dynamic, right? Because we haven't defined any of what like weights are, any of what bias is, but we could define it whenever we call it. So this is what makes object-oriented programming, object-oriented, because we're creating these objects to represent real values that we're going to plug in later. So now what's next? So we can actually go ahead and maybe call a layer. So we can just go ahead and create a layer really quickly. Alright, so we'll call layer gen. And then whenever we initialize it, we have to give the number of inputs and the number of neurons, like we specified. So we can go ahead and do like what? Like 3, 4, 3, 5. Let's do 3, 5. Right? And we'll also have to create a set of inputs as well. So we might as well go ahead and do that now. And usually your inputs, right, are going to be equal to X, that big X, capital X. That's how you represent your inputs whenever working with machine learning. So it's just something to remember. So we can go ahead and create a 1D array. So we can do 1 and -2, 3, 0, and 2, right? Actually, no, we have 3 inputs, so we can't really do that, can we? So all right, so why don't we go ahead and do this? And then we'll pass it that. So we'll say layer 1 dot forward, because we've already initialized it as a layer class. So you can call this function dot forward, and then we'll pass it X. Okay, and then we can go ahead and print that out, I guess. We can print our output out by maybe just calling it for, so we can do dot output. Should work. Alright, and it should print out the output. So let's see what we get. Oh, we got an error. Cannot interpret 5 as a data type. Self.rise. How's that not a good? Huh. What if non-neurons was 10? Oh, I see the issue. I see the issue. We just went over this and I still see the issue. Okay, there we go. Problem solved. That's right. Layer gen has no object attribute forward. Oh, we misspelled it. Perfect. Now we got our outputs. How amazing, right? Okay, so how many outputs should we have, right? We should have 5 outputs. That should make sense because we have 1, 2, 3, 4, 5. Yeah, we do have 5. It should make sense because we have 5 neurons, so we'll have 5 outputs for whatever layer we're looking at. We passed it 3 inputs, which it sent individually to all 5 of those neurons, and it returned these values, right? We have a problem there. Oh, what just happened? I swear to God, this ID is making me mad. Okay, so we have a problem. Most of our values are not normalized. So we're getting numbers like 2.221, 2.0416, and we're getting these numbers because these values aren't normalized, and because these values are not normalized. To normalize these values, we can just multiply by a scalar. So we can just multiply by like 0.10, something like that. So if we run this again, yeah, these values should be much smaller. And if we wanted to normalize this, we could just do the same, right? We could multiply by a scalar. And yeah, that's pretty much an object-oriented forward pass in Python, right? So you can make more than one layer. What if you want to make another layer? So say layer 2 is equal to layer gen, right? And this layer, instead, it has 5 inputs, right? Because the layer behind it, so this is layer 2, so this is the layer after layer 1. The layer behind it has 5 outputs, so this one must have 5 inputs, right? So it makes sense that it has 5 inputs. And the number of neurons, we can make whatever, so we can make this one 2. So this one has 2 neurons. And we'll create 3 layers. So I'll do this one more time. But this time, we can take 2 inputs in because the layer behind me has 2 outputs. So we'll have to take 2 inputs in. And then maybe we have 10 neurons in this layer. That's a lot. Let's do 4. So we can do this, right? And for every layer, we do have to run the forward pass. We have to like write out the equation or like write out or call the forward pass at least. Forward. And this is layer 2, so we do layer 2.forward. So yeah, we can do this every single time, right? This one layer 3, so we can do this every single time. And this is how it pretty much works, right? But instead of using X for layer 2's inputs, guess what we're gonna use? Layer 1 dot output. Sorry. So layer 1 dot output. And why are we doing this, right? Well, we can go right back to the handy dandy diagrams we've been using and take a look at this thing right here, right? So if we have 2 outputs leaving, or let's start from this layer. So we have 3 inputs or 4 inputs, sorry. No, sorry, 3 inputs, I'm sorry. 3 inputs going into 4 different neurons in the middle, right here. And these 4 different neurons do their thing. They get 4 different outputs, which means this output neuron right here, as you can see, has 4 arrows coming into it. It has to have 4 because there's 4 neurons in the layer behind it. So that's pretty much just a review about what we've been talking about for over the past couple of videos about how uh, there's some inherent properties to neural networks in that every layer has a connection. Every node in a single layer has a connection to every node in the previous layer. So it's just concepts like that we're going over again. So layer 2. So that layer 2 is going to be layer 1's output propagated to that layer again. Layer 3 we could do layer 2 output. All right, and then at the finale, we're going to print out the third layer's output. So what are we doing here? Let's start from the top. We have a set of inputs. We initialize our first layer to be 3 by 4, so it has 3 inputs and 5 neurons. We throw a forward pass through the layer, and then we generate the second layer. This one has 5 inputs and 2 neurons, because it has to be respective to the layer behind it. And we do a forward pass, but this time we send in the output for the layer behind it as an input instead of this. And then we do it again. So we make the third layer. It has 2 inputs, 4 neurons. We do another forward pass, but this time we send the output for this layer into layer 3. And at the end, we print out the layer 3's output. So I'm going to go ahead and run this. All right, so this is what we get. And it makes sense as to why these numbers are so small, right? Because we keep multiplying them by such a tiny number that we're getting up here. So it does make sense as to why the numbers are getting smaller. And it looks like everything is handy dandy and correct. So this is what it looks like, pretty much automating a lot of like the layer creating process. We can just ignore the code up here. So all this code up here was to do what this does right here, and what it somewhat does up here. But these two are unique in the sense that these are initializing it randomly. So we haven't done this up here, but they are initializing it. So these two functions are pretty much what this is, but they can do much more now because they're dynamic, and you can add however many inputs you want, add however many neurons you'd like, create these big neural networks and run some forward passes through them. All right, so that should be the bulk of something like the object-oriented programming part of this. But yeah. All right, so now that we can, kind of create these layers kind of automatically, not automatically, but we've simplified the process of creating these layers. There's still something we're missing, right? So in a neuron, like what are we doing right now? Before we even talk about that, what are we doing right now? Oh, we're just taking a certain set of values, right, an x, and propagating it through a neural network with no restraint, right? So we keep sending it through the neural network no matter what. So there is no threshold. There is nothing for anything to like go over for our neuron to fire. There's nothing like that. So we need to make something for that, right? Because in real life, when you have a neuron, it doesn't always fire with no restraint or with like no restrictions, right? It doesn't always fire. There's always there's like limitations as to when it will fire and because of what reasons, right? So there's like a threshold that these certain inputs have to cross for for an output to actually be received, right? So we call those activation functions in machine learning and neural networks. And what they do is they basically add variability to our model, right? Because without it, our model would simply just fail because it is a linear propagation through a network, right? Because if we don't have any activation functions, this is what our entire like model's math will be done by. Just summing up the weights and inputs. Summing up the weights and inputs and adding a bias to it from every single node from every single layer, and then on and therefore. So our let's see. So our model would kind of on general have a trend of like this. right? Or this. You can't really model anything well, just linear functions, right? So that's why we add activation functions, is because it adds variability and like control to our model. So if we added an activation function, our function could look like this. Something like that, right? In which it continuously keeps doing this and propagating, and it creates like these cool shapes that kind of can fit lines of best fit and stuff like that. All right, so let's quickly recap what we learned about activation functions. We know that they exist to kind of add some non-linearity to our outputs, so that we can model stuff that isn't linear, right? So if we have something that looks like a quadratic and we're trying to model it linearly, it's not gonna work out that well, right? So that's why we need these activation functions to kind of change the output so that we can model it using cool lines like that look like this, rather than using lines that look like this, which are kind of like general and too broad, and they don't really work that well at modeling some stuff. So that is why we use activation functions, and we care about two different activation functions for our purposes, right? This is the we just read rectified linear unit, right? ReLU. And basically what ReLU does is it is an activation function that limits your output depending on what your input is. So if your input, if x is less than 0, this thing will return 0. Else return x. So what does this mean, right? So it's basically saying that for every x value less than 0, it'll return a y value of 0. And once it crosses the threshold of 0, it'll start returning whatever x actually is. So you may be inclined to think that okay, this will never be a negative number, right? But it can definitely be a negative number, because isn't this the same exact thing except inverse if we just do this? So these would be negative, but it's still a rectified linear unit because these are still 0. It's kind of like above 0, but these are still 0, but these are negative, right? So you can have a rectified linear unit output, but you don't want negatives in your sigmoid, which is something over here. This is something you don't want negatives in. And the whole point of the sigmoid function exists to basically get rid of negatives at the end. So how does this really work, and what's the purpose of a sigmoid function, right? So at the end, when we're calculating percentage error, we need some sort of like quantifiable way to determine the error. So if we were just to do a rectified linear function, right? And we got to an output, any negative number over here, right, completely gets cut off. So say our neuron, this is our neuron. These are the two hidden layer neurons behind it. This is our final output neuron right here that I drew. So say this this thing was sending it -3 and this thing was sending it 2. This entire output would be called. It would just send a 0 because of this activation function, right? So this entire negative gets erased. So this thing becomes just this value right here. So it would its value would be just 2, right? And we don't like this. We don't like this because we don't like getting rid of negatives, right? We don't that negative still has value in our neural network. It still represents something. We just don't like the negative in front of it. But we need to represent what the negative means, if that makes sense. And simply getting rid of all the negative outputs, depending on whether or not they had negative inputs, right? That pretty much just gets rid of the entire meaning of that data. It just gets rid of it from the entire data set. So our final output won't have a good representation of like the percentage error because we're missing some key parts of our model. For the sigmoid function on the other hand, this is called the sigmoid function. This is unique in the sense that it converts negative inputs into a tangible and positive y output. So this does exactly what we need, right? It pretty much gets rid of the negative output, but it still lets it hold meaning. It still gives the negative inputs meaning, because it doesn't completely get rid of them like the ReLU function does, but it rather converts them into positive, infinitely small, positive, infinitely small, like output value, depending on how close you get to negative infinity. So this will never be a negative number as an output, which makes it really useful for us. So we would simply just do the opposite. So if we're gonna calculate it again, we could do actually no, we don't have to calculate it yet. Oh, we'll get to that later. But just for note for now that the sigmoid function, it allows us to keep the meaning of negatives in the neural network, which in turn allows us to get better error percentages and have better a means of backpropagation and error like fixing. Like the computer can kind of fix its errors faster and better if you use the sigmoid function. Okay, um, we will be implementing these, and we will okay. So for you can already see that the ReLU code, it won't be that complicated. You can already see that it kind of shapes out to be like an if statement right now. All right, so why don't we go ahead and figure out a way to model this, right? So we initially decided that this is what our ReLU is going to be decided by, right? So if the input is less than 0, return 0, else return the input. So it's pretty simple. We'll go ahead and code that up real quick. And so we can go ahead and create a different class for this, right? Because it's not a part of the layer generation. It's simply like you're gonna be giving it the forward pass, and then it'll simply call the forward pass if it's less than a certain value. So we can just go ahead and create a different class for it called activation ReLU, I guess. Activation ReLU. Alright, let's name it ReLU activation. All caps. You know how we are. Okay, so we have what do we have? Alright, so we still have forward. We still have a forward pass. We're still doing forward passes. But this time we're gonna be still giving it itself and the inputs because that's what forward pass needs. But we'll need to create an if statement to determine what the output's gonna be, right? So if x or inputs is less than 0, right? It'll return a 0, else return x or inputs. So that should look pretty normal. And so what this does is pretty much it looks at whatever inputs you're sending it through the forward pass. It sees if the input is less than 0. If the input is less than 0, it'll call the value no matter what the input is and return a 0. Else it'll return whatever the input is. So that is basically what this is right here. This is what we just modeled. And that is kind of like the longhand way of writing that out, right? So there's definitely a shorter way to do it. And that shorter way is by using something called or a NumPy function called maximum, in which it'll let me just write it out real quick just so you can see what it is. So we can go ahead and get rid of this if statement and replace it with this and what does this do? So this pretty much does exactly the same thing that we just coded, but in one line instead. All right, so basically it'll take a look at the inputs. If it's greater than 0, it'll return inputs. So it'll return the max inputs. It'll return inputs, and if it's less than 0, it'll call the value and return a 0. So we can go ahead and actually test run this, right? We can go ahead and see what this looks like. Let's get rid of this line of code, copy paste it quick. Um, and we can do that by quickly just calling the function, I guess. So we can just say test is equal to activate the class. So it'll be relu activation. There's no initialization parameter, so you don't have to pass anything to that. And then we could do test dot forward. That's the function. We'll give it the inputs. And the inputs we're referring to is going to be this right here, this array. So if we were to run the, oh, that's not good. Okay, so if we were to run the relu activation function on this, what should we get as our, oh, it's already up here, but we should be getting a 0, a 0, a 2, and a 3 if we run the activation function. And we know this because 0 and -1 are both going to equal 0 once the function does its thing, because -1 is less than 0 and 0 is 0. And 2 and 3, they'll do nothing to it because they're both greater than 0, so it'll just pass them forward. So if we go ahead and then run this test.forward inputs, and then we print our global variable, which is test.output, we should get 0, 0, 2, 3, and that makes sense. This 11.5 and 7.5 are from our earlier block of code. We can go ahead and get rid of this now, I guess. It's been a while. We can go ahead and get rid of that. This is our code now. This is what we're working with. And actually, we'll keep the inputs. Everything else, I think we're good. Getting rid of, yeah. So we'll do that. Okay, so we know that our relu function works, and that's all handy dandy, so we're good to go now. Go ahead and get rid of this. Put that back. So we're good to go. Alright, so now that we know that our activation function works, we actually have to apply it to our neural network, right? And the whole point of the activation function is to be applied like after the actual forward pass is done. So after it does the weights times the bias, weights times the input, sorry, plus the bias, then it'll take this output, send it to this activation function as the input, right? And then it'll cull any values that are returned that are less than 0 and or 0, and that's going to be our true output for that layer. So it's just like an extra step you have to do after this forward pass in order to get the true output of a layer. So right here, right? So we initialized the layer. We did a forward pass for layer 1. So we have to add an extra step now. We have to do we have to actually create the activation function first. So we will create an instance of it real quick. We'll call it activation 1, I guess, is equal to relu activation, and then and remember how we, what am I doing? Remember how we don't have to put any parameters in there because we haven't specified anything for our initialization like we did up here, so we don't have to pass anything to that. Then we can do, now that we have it initialized, we can call it down here. So we can do activation 1.forward and then pass layer 1.outputs. So we're basically taking, so we're running the forward pass for layer 1. So we're running this, and then we're taking this output, the self.output that it returns, which is the dot product of inputs and weights plus the bias. We're giving it to this function right here. So yeah, we're giving it to the forward pass for the activation function, which is right here. So it might be a little bit confusing with two forward passes, but they're for their respective classes, so they'll never be able to, like, you know, commingle, and you'll know what they belong to because they'll be attached to their respective, you know, objects that we created. So for the activation forward pass, we'll throw in the output for the layer gen forward pass, and then after that it'll pretty much do its thing. It'll get its own output, and that's the true output we want. This is the true output that we want from that first hidden layer. So then we can write output 1 maybe. Actually, we don't even have to do that. We can just continue on by replacing this with layer 1 output because we changed it, right? We added an activation to that output. So now we have to change it from layer 1 output to activation 1 output. So that becomes our true input now. So we'll do the same for this one as well. But we'll also have to create a different instance. Activation 2 is equal to rel u activation. Let me spell that. There we go. Okay, so they're both activated. This one's being called after the first one. Now we have to write activation 2.forward. So we're taking the layer 2 outputs now. Let me put some spaces between them so you can see the differences. So just like in layer 1, we run the normal forward pass, then we run that activation function on the output for that forward pass. We do the same thing for layer 2, run the forward pass, and we run the activation function on the output of that forward pass. So layer 3, same exact process, but we're just going to copy paste it because I don't want to rewrite. Activation 3. Okay, so we have our activation 3 is equal to the forward. Why does it keep doing that, man? Because activation 3 is equal to the or we run activation 3 on the layer 2 output, and that should be good. That is not what we want. It's not layer 2. It is layer 3. We want the layer 3 outputs. There we go. So it corresponds activation 1 to layer 1, activation 2 to layer 2, activation 2 to layer 3, layer 1, and we're passing it the initial input. And for this, we're passing the activation input or output. For this one, we're passing the same activation output, but for activation 2. Okay, so we're doing everything correctly. So if we print out not layer 3 output, if we print out activation 3 output, we should get something that's a little bit different. Layer gen object has no attribute outputs. Attribute 2. Layer 1 dot. Outputs output. Okay. There we go. 1, 2, 3, 4. Exactly how we expected. So, wait, 1, 2, 3. Wait a minute. Let me run this again. 1, 2, 3, 4. 4 neurons at the end. Perfect. Yeah, okay. So we did it correctly. I was a little confused because I forgot that we specified that we had 4 neurons at the end. Alright, so perfect. That works. Alright. So that's how you implement an activation function, and you might be thinking, oh, what's the point in doing this? But they are very essential, especially considering the fact that not everything in the world is linear, and we have to model those things that are not linear. So these are really, really essential, and the rectified linear unit is currently one of the more popular activation functions. And so yeah, this is how you implement it pretty much. Oh, I forgot to mention that we know that the activation function worked properly because we're not getting any extraneous values that are less than 0 and negative. So everything is positive, and that's a good sign that our activation function actually works. So everything's looking handy dandy, awesome. What did I just say? So everything is looking good, and that's pretty much how we know it worked. If you want, we can actually go ahead and print the layer 1 activation or layer 1 output before the activation 1 output, just to see what values get changed into 0 and what stayed the same. And yeah, that's pretty much now finally that's actually pretty much it. Alright. All right, so similar to the sigmoid and ReLU functions, there's also one more activation function that we should go over. It's called the softmax activation function. And this is a pretty important activation function in the sense that it converts like vector whole numbers, right, in an array. So these whole numbers in an array into probabilities as an output. And you guys can probably already understand why this is essential in neural networks, right? Because we usually want to solve for probabilities, or we need some sort of probability as a result of the neural network, right? So it's always good for the output to be a probability, and it's also good in this sense because now we can compare these probabilities and actually improve on itself because none of the nuance is lost. And what do I mean by that? So because we're taking the exponential of the input, right? It's gonna be the same as the sigmoid. You don't lose any nuance to the negatives. So you don't get any so if your input is negative, right? You don't return just a zero. You'll still return like a value that has some sort of representation in the data set. So that means you're not losing any nuance. So if you're say you were using a ReLU function, right? And you had a negative 30 value going into the function. It'll come out with a zero, right? As expected. But what if you had a negative 1 million, right? It'll still come out with a zero. The outputs will still be the same no matter what ginormous gap there is in between the data, right? So you lose all the nuance between your data in there. So some of the some of the relationships of the data are kind of lost when doing that. And we don't really like that happening when we're solving for our final output, right? So to mitigate this problem, we'll use exponentials to still keep the meaning of the negatives, right? Because negative exponentials are still equal to something, but they are still positive, which we're looking for. So, and they're going to be above zero, which is something that we want because we want to keep the relationships there, but we don't want any negatives as our outputs. So this is what we do. The softmax activation function basically exponentiates uh, the inputs, and then it normalizes the inputs. So basically, that's what this is doing right here. And normalization is basically whenever you divide a specific value by whatever whole value it belongs to. So this in this scenario, it's basically saying that each of these inputs is going to be divided by the exponentiated form of that input. So this would be e to the 1.3 in this scenario. Let me write this out actually. So we'll have e to the 1.3 divided by the sum of e to the z j times. So basically what this equals is e to the 1.3 plus e to the 5.1 plus e to the 2.2 plus e to the 0.7 plus e to the 1.1, and you divide e to the 1/3 by this entire thing, by this entire sum down here, to get this zero point 0.2 probability right here. And you do that for every single input. So the next one would be e to the 5.1 divided by all of this. The next one would be e to the 2.1 divided by all of this. E to the 0.7 divided by all this. E to the 1.1 divided by all this. And you get these probabilities as your output. And because you're normalizing it, the sum of all of these should be 1. So you have 0.2 plus 9, 0.9, so you get 9.92 plus 0.5, so 0.97 plus 0.1, so 0.98, and then plus 0.2, 0.02, so you get 1. So the sum total of all of this is 1, which makes sense because it is normalized. And we're looking at probabilities. So the softmax activation function is pretty much only going to be used on the final layer of your neural network. So it's going to be used on the output layer. And this is pretty much how the computer determines what's wrong and what isn't. It's a really good way of doing that rather than using a ReLU, which kind of kills the nuances and the negative numbers. All right, so that's what a softmax activation function is. Why don't we go ahead and start coding it then? Start representing it in our code. All right, so I went ahead and recreated another Python file real quick just so we can get rid of the clutter and just focus on modeling our softmax function before actually putting it into the big code. So why don't we go ahead and go back to the actual code. So as as we noticed earlier, there's a couple things we have to do. We have to exponentiate these inputs, so we have to take e raised to these inputs. Then we have to normalize that exponentiated value, and then that's what becomes our output, right? So how do we do that? Well, we can do it two ways, right? We can either just set e to equal Euler's number, which is like 2.718 ish, um, 2.718, like 28 or 29 or something like that. So I think I should leave it like that. Um, you can either set Euler's number to be equal to a set value, and then just do maybe output is equal to inputs, or e for the inputs, and then print output maybe. Try that. Yeah, that works, right? So you could do that, or you could also import math library from Python, and then just do e equals math dot e. Actually, you don't have to do that, I think, because you don't have to do that. You can just call the exponential function from math, or for NumPy, right? So you can just do exp values, or exponential. Alright, exponential values is equal to np.exp. So it exponentiates. What am I typing, man? It exponentiates our inputs, and then that's for the first step done. And so now we still have to do the normalized part, in which, so we just did this, right? We just did this. So now we have to do divide by the sum of everything. So that's something we have to do as well. So why don't we go back into our code, and we'll say normalized exp is equal to exponential values divided by np.sum of the exponential, right? So this should be exactly what we're looking for. So why don't we go ahead and print normalized p. Okay. And we can also check to see if it works properly, because we know it's normalized, so the sum has to equal 0. So we can go ahead and do the sum of normalized exp and print that out as well. And this printed out should be something really close to the value of 1. Oh, what's going on? That's odd. Huh. Maybe it's just sum. Why is it not printing that out? What is that printing, man? Okay, that's a little weird. Alright, I'll be right back after I troubleshoot this, I guess. Alright, so I figured out what the problem was. I forgot that you can't individually run cell segments in this IDE. So I was running the main when it was supposed to be running just that little file, but it wasn't doing that. So, um, alright, let's see. Okay, so we can just go ahead and recreate it here, I guess. So we'll do the same thing. We started off with exponentiating the values, so we can write exponential values is equal to the np.exp, so the exponential function through numpy of inputs. That's good. And then normalized exp will equal the exponential values divided by the np.sum. And that just divides by the sum of all of those exponential values. And then we can print p and then print the sum of the normalized. Go ahead and do that. Okay, yeah, perfect. So this is the normalized exp right here. And this is the sum of that, which is 1. So it makes perfect sense and it works perfectly. So this is good. So now that we have this coded out like that, we can actually, why don't we actually turn into object-oriented programming, right? Like we did for the ReLU activation. Why don't we do the same for this softmax activation, right? I think what would be smarter to do is actually create an activation class for all of the activation functions, but we can for educational purposes we can stick this for now, I guess. So we'll do class softmax, then we'll forward, and we'll have the self and then inputs, obviously pretty much the same as the top one. The output will equal, alright, don't focus on the output first. Alright, so we have to do this. Why don't we just move this up? So what we're doing is setting self.exponential values. Actually, yeah, why don't we do this? We'll make it all in one line of code instead of splitting it up like that. So what we're doing is taking the exponential of that input divided by np.sum of actually we can't do that because we need exponential values. We could just make a temporary variable, I guess. Then we'll say that and I can't type, equals np.exp inputs, and then we'll do divided by the sum of the exponential values. Okay, so that's pretty much exactly what we did down here, and we're just getting rid of the setting it equal to the normalized exp. So yep, it's exponentiating all the inputs, then it takes those exponentiated inputs and divides it by the sum to get the normalized values. That is exactly what we want. So that is our softmax class, and we can go ahead and actually apply it to the last layer if we want. So we can go ahead and create an instance of it. So we can say softmax action. So and since we'll probably only have one softmax per neural network, right? Per layer, per like output layer. We don't really need to specify how many there are. So softmax. There was no initialization parameters for softmax, so you don't have to specify anything. So we'll go to layer 3. That's our output that we're about to send to softmax. So that's what ReLU returned, and we're taking whatever ReLU returned and we're sending that to the softmax function. So how do we do that? We can go ahead and just say that soft dot forward, and then we'll pass it our inputs, which is layer 3 dot outputs or output. And then we can actually go ahead and print, it's already down here. softmax activation dot output. All right, perfect. And then why don't we go ahead and do this? Print sum of there we go. So yeah, it equals 1. Perfect. So we have yeah, that looks good. So there's a 25% chance, 25% chance here, 24% chance, 20. So these numbers don't really mean anything, right? Because our data is like our data is 3 numbers and they don't really have any meaning with each other. So there's no correlation in the data. So these don't really mean anything percentage-wise, but this is what it would look like at the end. The sum would be equal to 1, and these would be the percentages up here. So what have we done so far, right? We've taken this input, propagated it through a 1 layer, called the ReLU activation function on that layer. There's output, sent that output to layer 2, did the same process, called the second activation function, the second ReLU, to layer 2's output. Then we sent that straight back down to layer 3, did the same exact process, and our ReLU, actually, if layer 3 is our final output, we don't really need to do ReLU beforehand, actually, so we can get rid of this. If this is our final output layer, we don't need ReLU on it, so we can get rid of that, and actually go ahead and, yeah. Yeah, our code would work either way, because look, we weren't using the activation 3 output as our softmax activation. We were using the actual value we were supposed to use, which is layer 3 output. So we did it right. So we can just get rid of the activation function for ReLU for layer 3 because we're not using it anymore. We're replacing that with softmax. And yeah, this should be right. Should be the same number still. Oh, they're changed. How'd it change? Huh. Oh well, this is what it's supposed to be like, I guess. But that's close enough to 1 for us to be fine with that. So this is what these right here. This is just us calling layers into existence and then working and creating a neural network. Everything up here is how we're able to do it through object-oriented programming. And yeah, that's what a softmax function is pretty much. Alright, so it's going to be a quick cut because I found a couple errors in the code and I went ahead and changed it. So they all stem from the softmax function right here, and there was 2 errors. One was that the exponential values, right? We didn't have like we didn't have an overflow for 'em. So since we're working with exponent, usually this would not be a problem, right? Because we're working with linear functions, and the overflow for this computer is like huge. The number is huge, and it's like tens and tens of digits, right? It takes for the number to actually overflow on the computer, and we'll never get that big of a number using any linear functions, right? But in this case, we're using an exponential function. And we can go ahead and see how that kind of goes out of hand very quickly, right? So if we have the exponential function raised to like the 10th power, we get this big number already, right? It's already a huge, huge number, right? But say the number was 10 times bigger, it was 100. Somehow our neural network ended up with an input of 100 in the neural network in any of the nodes, right? If we run this, we get this number, right? And that's 43 digits after 2. The computer cannot handle that. There's no way it can handle numbers that get this big this quickly, right? And because that's the case, we have to include sort of an overflow statement, right? And that's pretty much us taking every input and subtracting the max input from that set of inputs. What that basically does is ensure that no number will ever get to that gigantic value that overflows the computer, okay? So the npmax function has 3 things. It has the inputs. It tells you where you're getting the max from. So we're getting it from the inputs array. it tells you how you want to calculate the inputs, which basically means whether or not you want to get the inputs from the rows or the columns, right? And axis 1 just means we're pulling the maxes from the rows. I'll explain that in just a second in more depth. But continuing on, the keep dims, this part, it basically just says that you want to keep the dimensions of whatever the original array is, inputs. You want to keep them the same when you're returning the maxes. So I'll explain these two concepts like right now, actually. So basically, let's say we had inputs that we had an inputs that were two array. It was a 2D array of inputs, right? So we had 2, 3, 5, and 6, and then 6, 1, 2, and 3. Right? So this is a 2D array. Okay? These are our rows. You can kind of see it like that. These are our columns. We have 2 rows, 5 columns, and when we pull the np max function, right? So say we did np dot max of this array, we'll call it array, and we said that axis equals 1 and keep dim equals true. This is what we're going to return, right? We're going to look for the max in every row, right? Because we're looking by row. It's specified how to look, right? So we're going to find the max in every row. So for the first row, it'd be a 6 right here. And the max for this row would be a 6 as well, okay? And, oh, these are kind of bad numbers, actually. Hold on. I'll change this 6 to be a 7. So the max for this row will be a 7, because 7 is the greatest number out of all of these numbers in this row, and 6 is the greatest number out of all of these numbers in the row. And so it'll pull a 6 and a 7, and then it'll look to see if the dimensions are kept true. So since the dimensions are kept true, and we have an array that has 2 rows and 1, 2, 3, 4, 5 columns, right? A 1D array only has rows, right? Or only has one. It doesn't even have rows or columns. It just has elements, right? So since we're calculating by rows and it's asking us to keep the dimensions true, we know we're gonna have 2 elements as the final like output, right? Because we have 2 rows to calculate from, and we're pulling 1 max from every row. So we know that there's only gonna be 2 elements left. And keep dimension just lets you know that it wants the values, right, to be kept in their own 2D arrays. So it would be a 6 for the first one, and then a 7 for the second one. If we did not keep dimensions, right, if we had not turned that on, this would be the output. It would just be a 6 and a 7. It would just be a 1D array. And keep dimensions just keeps the maxes in the same format, so it's still a 2D array. And if we didn't have axis, let's say we just got rid of axis, right? We got rid of this, and we only specified that keep dims was true. It's going to return the max of the entire 2D array. It's going to look at every single element in the array and just find the max. So the max for this array would be not a 2, not a 3, not a 5, not a 6, a 7. It would be a 7 right here. It's the biggest number. So the output for this would just be a 7. And actually, no, it would be a 2D array with just 7. And that's it. Let's say we we set the axis to equal 1. Or 0. 0, sorry. And keep dims was true. It'll take the max for every column, right? And we have 1, 2, 3, 4 columns, so we know we're gonna have 4 elements in this array. So how would that look, right? We would have a 2D array, because we're keeping the dimensions true. We would have the max for every column. So the max for the first column would be a 7. The max for the second column would be a 3. The max for the third column would be a 5. The max for the fourth column would be a 6. And then this would be our output, right? And visually, it kind of makes sense as to why, when you're calculating it by rows, you might get like this, right? As opposed to calculating by columns when it looks like this. Because by columns can kind of see how they're like the columns had like the first element in every column. It's at the top. There's 4 columns. You can kind of see how these are like the first elements in every row and how there's 2 rows. So it kind of makes sense as to how the outputs look when you keep the dimensions. Alright, so those were just a couple of changes I made for the exponential values to add like an overflow statement. And for the other part, the output, we also added another line of code. We did the same exact thing, right? We specified what we're going to sum. Instead of maxing, we're going to be summing this time, right? So we just specified that we're going to sum the rows, keep the dimensions true, and we're going to be taking these values from the exponential values array. So we're going to be summing every row in the exponential values array, and then returning it in the same dimensions as we just discussed. And then because this exponential values and the sum, right, of exponential values have the same dimensions as we said as we initialize the keep dims to be true, right? We can actually use do some math with it. So we can subtract and divide element by element. So we're not going to be dividing like a really big array with a really small array. We're going to be dividing the same size arrays, if that makes sense. Or the same dimension arrays, not size, because the maxes might only return a couple of values, while the entirety of like the exponential values array has like hundreds of values. So, but they still have the same dimension, so they still look the same like this, right? This still looks the same as this, but it doesn't have the same number of elements. If that makes sense. And so if you were to subtract this from this, you'd subtract. If you subtract this tiny array down here with this big array up here, you'd get like 2 minus 6, 3 minus 6, 5 minus 6, 6 minus 6, and then you'd get 7 minus 1, 1 minus 1, 2 minus 1, 3 minus 1, and that would be like the big array output you'd get. Hopefully that makes sense. Okay. So those were just a couple of changes we had to make to the softmax function to make it actually work. Because when we're trying to get the output, we're not trying to get the output for the entire sum, right? We're not trying to divide by the entire sum of the inputs, right? Because the inputs represent more than one layer, right? The inputs represent multiple batches, kind of, because these 2D arrays, they work like this. You're sending 1, 2, and 3 first into the data set, then you're sending 4, 5, 6 later. So these two are kind of independent from each other. So 1, 2, and 3 are kind of independent from 4, 5, and 6. So we want to sum by rows to make sure we keep that independence in the network. So we keep that correlation in that network, and we're not just dividing by the sum of the entire set of inputs, which is not what we want. So we had to include that for this output. And when we run this, it should run perfectly fine. And you guys can kind of see how like this last line of code that we just discussed, like, you know, some of the concepts we just discussed is visible up here. So it's printing the sum of the softmax activation output, right? So it's printing the sum of this, and it's printing by rows, and it's keeping dimensions true. And we discussed earlier how the softmax output is basically a percentage probability. So it's going to be like its whole sum is going to be 1. And when we print out the outputs, both rows are equal to 1, so we know that it works, right? And we have 2 rows in this case because we had 2 sets of inputs going in. Or like the last layer, right? Had 2 sets of inputs coming in, right? And so that's why we have to specify what we're summing and doing our math by, because our inputs don't just represent one set of inputs. They represent like multiple sets of inputs. And in this case, our set of inputs x, they represent 2 smaller sets of inputs. So 1, 2, and 3, that would be 1, and 4, 5, and 6 would be 1 as well. So we have to kind of like specify what we're doing the math with, because we don't want to be doing the math with every single number in the array. We want to be working with sets of numbers. Yeah. Alright, so that's pretty much it for video 3. We basically turned the code from last video into object-oriented programming. We introduced the rectified linear activation function, the softmax function, and then we modeled a forward pass using these 2 batches. The first batch being 1, 2, and 3, the second batch being 4, 5, and 6. And that's pretty much it, right? Next video we'll be taking a look at loss and optimizations, which is pretty much how backpropagation, right? Um, we won't be going it through the Khan Academy style that we've been doing so far, in which I like explain uh in like the in this document, and then I also explain in like in the actual code, right? So like what we'll be doing is just taking a look at a completed neural network that has backpropagation and optimization and loss incorporated into it, and then we'll be breaking it down from there. So we'll start from we'll reverse engineer it basically. Hopefully that's a little bit easier to understand than just starting from ground up, because some of these concepts that we're about to go into are these are the real hard concepts of machine learning. What we've been of neural networks and machine learning. Sorry, what we've been doing so far is very complicated, and it's still like difficult to understand as it is. But we're going into a different league now because we have to talk about some advanced math, use some little lengthy equations and stuff. So we'll start backwards next video. All right, so see you guys then.